Welcome to Queens College Physics Department's online lab sequence. This is DC Circuits, Lab 5 in the current progression. The objectives for this lab are to help you get a little bit of experience building basic circuit technologies from circuit diagrams, series parallel combinations. To use Ohm's law to analyze simple circuits, and to test a theorem that any resistive DC circuit can be reduced to a voltage source at an equivalent resistance. The resources for this lab are the Google document you're now reading, which can be downloaded from the Blackboard assignment, a short introductory video which you are now watching, and the FET circuit construction kit, which we're going to see in a moment. The FET kit is a simulation provided by the University of Colorado. The FET site is extremely popular for science labs for simulations. We donate to them to thank them for allowing us to use this course, but it is of course free other than that. The simulation kit allows you to build circuits, measure voltage, current on various components. The one thing it doesn't do is it doesn't measure resistance directly. So you'll have to use Ohm's law to calculate resistance in circuit elements and use the appropriate formulas to reduce circuits to equivalent resistances. To start, I provided the values, the nominal values for R1, R2, R3, R4. And that's enough to start. For the report, in the abstract, just answer these three questions. This is looking for an intuitive response, what you think you know now. The idea is for you to get it down so that you can compare what you now believe later after you've done the lab. For equipment, the first part of the lab, or the demonstration of the site, I'm going to talk about some of the particularities of circuits and of that lab. So, and you should write about those. The 3 points here are 3 things that should appear in your report. You'll see later as I go through the demonstration. Data. All your data are going to be measured currents and voltages. Then you're going to calculate resistances. It all should be tabulated neatly and probably in such a way that you can make it obvious how the resistance is changing, overall resistance is changing, and as you add resistances to the circuit. You should also, for each procedure, once per each procedure, provide a screenshot of a circuit from the site. There's a button in the corner of the FET site that allows you to take a screenshot. This is just to show that you've actually done it correctly. For analysis, you're going to be taking the calculations for effective resistance and using the nominal values that I've given you, and you're going to compare it to the measured values using percent error. You should show one sample calculation for each of the procedures. You can do this by writing it out neatly and scanning it into your report. At the end, in conclusions, you'll see at the bottom of this document, it brings up several things that you should discuss and or answer in the conclusions of your report. And that's it. The introduction here is material that's covered in your lecture course and in your textbook and in a million places on the internet, and you can read through it on your own time. And that takes it to the procedures. So I want to go directly now to the FET site. I can do that using this link. And here we go. The site opens up like this. There are 2 viewing modes. In one mode, you can look at pictures of things like this. I find that a little busy, and since we are going to be providing circuit diagrams later, I prefer just to have the circuit diagram icons. So let me build a very quick little circuit here. A resistor. This is a battery, a resistor, and wires to connect them. And immediately you see the little blue dots with negative signs running around the circuit. So the battery has a long and a short side on the icon. The long side is the positive side, the short side is the negative side, and that's why you see the electrons flowing in that direction. The resistor doesn't care, it's a non-polar component. It works no matter which direction the electrons are flowing through. The difficulty here is that when we're working with circuits, we don't use electron flow. Electron flow is handy for physics because it's what's actually happening, but because of historical accident, we measure things in conventional current or the direction of positive charge. You can simulate that here by going to conventional. Now we have red arrows showing the positive flow of a current. The size and speed of the arrows are indicative of the values for that current. That's not very informative other than to show the direction, and it's not enough for us, certainly. And again, I find it pretty busy, so I shut it off. There is a value here for labels, which you can turn off, but that simply hides the names of the components, and that's not the kind of guessing game we want to play here, so you should just leave it on. Values is important because it shows you the values for each of the components in your circuit. These are the components. There are more because you see the arrows, but we're only interested in the ones on this page, and then not even the light bulb. A wire, a battery, a resistor, and I'm going to use a switch. How do I use a switch? Well, I'm going to click here, which brings up a pair of scissors, and I do that and it breaks this. I can now bring out the switch and move it close. It will automatically snap into position, and I can do that. So the problem with that is the snapping is it's not always the neatest, and you should try and be neat here because you're going to have to take screenshots. When the switch is open, this is an open circuit, the infinite resistance. When it's closed, it's a closed circuit, and you now have current flowing. Open the switch, and it's not flowing. That's all you can do with a switch. The values you see here are the default values for the components. A battery by default has 9 volts, but if you click on the icon, you get this little box down here, and you can change it, and this is something you're going to have to do. You can use the slider, you can use the arrow keys, whatever you like, to set the voltage specified in the Google Doc. You can also change the polarity of the battery. Remember I said long was positive that side, negative is negative this side, but if I click on this button, it gets switched. If I now show you the current, well, I have to close the switch. The current is moving in the other direction. Now what is not shown here are the values for the resistance of the wires. So you've just completed the resistivity lab, and you should know why this is so. They do provide us with a way to change wire resistivity here, and that provides us with an opportunity to demonstrate it again. The resistivity here is set to tiny, and by tiny they mean practically 0. How do we see this? Well, let me break this and get an ammeter and connect that. So it's 0 amps because I have an open circuit with infinite resistance. If I close it, I now have a 1.5 amp current. Ohm's law, 15 volts, 10 ohms, it's going to give you a 1.5 amp current. So that means that the resistance in these wires must be 0. And of course, that's not true. If the resistance in the wires is not kept to some negligible value, if there is lots, then my current changes noticeably. Worse, let me add another node here. If I lengthen the wires by stretching them out, the current changes depending on the length of the wires. And we do not want to spend our time in electronics measuring the length of wires and determining what the resistance is for those wires. So we want the resistivity to be extremely low, so the resistance is negligible. However, we don't want it to be zero. That's completely unrealistic and will lead to calculations with no experimental error. So for your lab, you should nudge it up just a little bit. Here I've gone to 1.49, 1.47, 1.48, 1.49, I don't really care, as long as it is kept small. It should be negligible compared to the resistances used in the circuit. And that's wire resistance. Battery resistance is a topic we may not have talked about before. What does resistance mean in a battery? A battery is not a wire, it's a tube packed with some electrolyte, and it undergoes a chemical reaction to deliver electrons to the negative end. If you provide a path from the negative end to the positive end, the path will have a voltage on it, a potential hill, and the electrons will fall down that hill and go around to the other side. This is beyond the scope of the course, but a battery has an effective resistance. The resistance is caused by something other than resistivity. Doesn't matter what, it has a resistance. We ignore it because, of course, it needs to be negligible if you're going to have an efficient battery. We're going to let it set to zero. We're simply going to ignore the issue, just so you know. So here I have a circuit. A question is, if I open my circuit and I remove this and connect this. Now my current is zero because I have infinite resistance. This is an open circuit. But I have a battery connected to itself. The ammeter doesn't affect the current by definition, and the switch doesn't affect the current other than being open or closed. So this is a short circuit. This 15-volt battery will push out electrons that direction, but we're going with conventional current. We'll create a current in this direction, and there is nothing to impede its flow. So you should take the time to think about, and you can try doing it if you want, what the current is for 15 volts and zero resistance. Use Ohm's law and see if you can do a calculation. Tell me what's wrong with that calculation. This should appear in your discussion of the report, one of the items that we talked about earlier. I'm not closing this switch because I want you to see what happens when you do. Real life is not as spectacular as this because, of course, batteries have significant amount of resistance built in. It's still not a good idea. You should not do it under any circumstances. But that's going to be something for you to put in your report. Take a screenshot and discuss what I discussed for wire resistivity, battery resistivity, short circuits. So the only thing I have left to show you now is a building of circuits and measuring the voltage. I've shown you measuring the current. Well, let's go back and build a circuit. In fact, this little orange button with the swirl is the reset button. Click it and you go back to the beginning. But fortunately, that means I also have to change all this stuff. There. So I'm going to have a battery. I'm going to put positive down, and I'm going to add a series of wires. You'll see why, I guess. mostly because I want to keep it neat, but also when I show you what's going on. If you want to build a circuit, and all circuits of course can be reduced to a simple series circuit with a power source and a single resistor, then it makes sense to think of building circuits in terms of that kind of a circuit, a simple loop. Now, a simple series circuit would look like this. And I've forgotten my switch, so I'm going to use the switch to close it. Okay, not neat. You have to do a better job than me. Now, if I close the circuit, I now have a closed circuit with a path, and I will have a current flowing. You can bring in an ammeter to measure the... Actually, let's just delete this, and I can use the ammeter to close this. There. I have an ammeter with a measurement of the current. Now this current, of course, has a direction. If I show you briefly, that's the direction. Now if we were in the lab measuring current, we would find that if I did this, reversed the flow of current through the ammeter, it would be negative. And here it is not. This is measuring the magnitude of the current, but it is not showing you the direction. For direction, you need to think about the arrows or work it out for yourself, which is probably more useful. So that's a little tangled. Let me fix that up. And now the question is how to read the voltage. So this is a voltmeter. It has probes. If I take the negative probe, the black probe, and put it on the negative of the battery, the red probe on the positive side of the battery, I get positive 9.00 volts. That's because the current, conventional current, is flowing in that direction. Now there's only one other element in this circuit element, and that's this resistor. So if I follow along and put the probes on in the same sense, I will get a negative voltage. It's not the same voltage because we introduced some experimental error with the wire resistivity, but it is very nearly the same. It is negative because the resistor is dissipating the energy provided by the battery. Now, you should pay attention to this. It's not going to make a difference in this lab. It will make a significant difference in next week's lab. But that's how you measure voltage. So, I should be able to delete that thing somehow. I don't know how. Anyway, now what happens if your circuit is more complex? Well, if I wanted to increase the number of resistors in my series circuit, it's just a matter of adding a resistance in series. Series meaning there's only one path for the electrons. So if there's only one path for the electrons, then the current has to be the same everywhere. And because these resistors are the same, Ohm's law will tell you that they share the voltage that's introduced by the power supply. The tricky part is what happens now if you want to add a parallel element. Well, parallel element means there has to be a junction in the switch. So I want a branch here, and I'm going to put another resistor. And I'm going to connect it with a wire. So you'll notice that I made this series circuit first, and in the diagram that I was thinking of in my head, this had nothing attached to it, this had nothing attached to it, but this had a parallel resistor. So I created a second loop where coming from this node or junction. This is the key difference between a series circuit and a parallel circuit or a combined circuit. Everything but a simple series circuit will have a junction. And if you think in terms of loops, then you should be able to build your circuits correctly each and every time. When you're trying to resolve a circuit, to reduce it to a single equivalent resistance, you have to do this process in reverse. Many students will start here saying, well, this is 9 volts, then we have a resistor, and then they get stuck here because they have to decide which resistor is in series with these elements. And that's a nonsense question. Neither one of them are in series with it. You have a junction here. You can't talk about series circuits with a junction involved. You have to reduce this loop first. Use the parallel formulas to reduce this one to a single resistor. And you eliminate that junction, and now you have a series circuit, something with no junctions. And you can simply add the resistance to get the equivalent resistance. And that's it. That's all you need to know for the lab. Everything else is in the Google Doc. And you should be good to go. Next week is Kirchhoff's law, slightly more complex, but using the same simulation. So take the time to get this one right, because that will help you when you get to the next one. Have a good week. Bye.